This is the third video in the playlist of stereoisomers. In this video, I am going to discuss the types of stereoisomers, that is classification of a stereoisomerism, definitions of a configurational and conformational isomers. Understanding the definition is very much important. Rotation of a CC single bond, how CC single bond rotation is possible. Rotatable and non-rotatable bonds, which are also known as flexible and rigid bonds. What are the examples of rotatable bonds and examples of non-rotatable bonds? Rigidity of a CC double bond and CC single bond in the ring system. So these are the different subtopics I am going to discuss in this video. Stereoisomers are actually classified into two types. They are configurational isomers and conformational isomers. Configurational isomers are further classified into two types. They are geometrical isomers and optical isomers. But in this video, I am going to give the complete definition of a configurational isomers and also definition of a conformational isomers, and rotation of a CC single bond, rigidity of a CC double bond. So this is the classification. So first, let us understand the exact meaning of a stereoisomers. Stereoisomers. So here, stereo, the exact meaning of a stereo is a space. Therefore, stereoisomers are also known as space isomers. So these are the compounds having same molecular formula, same connectivity, that is the same structural formula, but they differ in spatial arrangement of atoms or groups. So in case of stereoisomers, of course, isomers, whenever you say isomers, they have same molecular formula. Here not only molecular formula, structural formula is also same, but they have difference in the arrangement of atoms or groups in space. So let us understand the definition instead of reading it again. Here you can see the two molecules. This is the first one and this is the second one. Here it is a 6-membered ring with two methyl groups at 1 and 4 positions. This is also a 6-membered ring with two methyl groups at 1 and 4 positions. Molecular formula is the same, structures are also same, but the difference is at this position, at this carbon, methyl group is above the plane and the hydrogen obviously that is below the plane. In the second representation, if you see, the methyl group is below the plane and the hydrogen is above the plane. They have same molecular formula, same structural formula, same connectivity, but here methyl group is above the plane, methyl group is below the plane. Spatial orientation of methyl group is different. Even spatial arrangement of hydrogen is also different. Here methyl is above, here methyl is below. Therefore, these two are said to be stereoisomers. Let me take one more example. Again, if you observe the pair of these two compounds, here in the first structure, if you see one of the sp2 carbons, one of the double bonded carbons, here ethyl group and hydrogen spatial orientation you can see, and here ethyl group and hydrogen you can see the spatial orientation. Here hydrogens are same side, but here hydrogens are opposite side to the double bond. Same molecular formula, same structural formula, but arrangement of groups, arrangement of ethyl group and arrangement of hydrogen, the spatial arrangement of groups and atoms are different. Therefore, these are also known as stereoisomers. Let us take one more example. This is the first molecule and this is the second molecule. You can check they have same molecular formula, connectivity is also same, but at this center OH group is right side, but here OH group is left side. OH group is right side, OH group is left side. So these are also known as stereoisomers. One more example you can see. So these are the two examples having same molecular formula, same structural formula, but at this position you can see OH is right side, but at this position OH is left side. Therefore, these two are said to be stereoisomers. So finally, in case of stereoisomers, they have same molecular formula, yes, same structural formula, same connectivity. Structure is the same, means obviously connectivity is same, but a different spatial orientation of atoms or groups around stereo center. That means we are introducing one more term, that is stereo center, stereogenic center. We'll understand the definition of stereo center and stereogenic center in the next subtopic. So these are the characteristics of stereoisomers. Now let us take the types of stereoisomers. Stereoisomers are classified into two types. They are configurational isomers and conformational isomers. In case of configurational isomers, the stereoisomers which are not interconvertible at a room temperature. That means here I am taking A and B. These are stereoisomers, let us assume. At room temperature, A is not converted to B, B is not converted to A. The interconversion is not possible. Why interconversion is not possible? All those things I will discuss clearly in this video in the next subtopic. A and B are stereoisomers. At room temperature, A cannot be converted to B and B cannot be converted to A. There is no interconversion. Therefore, non-interconvertible stereoisomers are configurational isomers, and these configurational isomers are again classified into two types. One is geometrical isomers, second one is optical isomers. So this is the exact definition of configurational isomers. In case of configurational stereoisomers, there is no interconversion at room temperature. Second type of configurational isomers, they are conformational isomers. These are the stereoisomers which are interconvertible at a room temperature. Now I am taking X and Y. These are stereoisomers, but at room temperature, X is converted to Y, Y is converted to X. Not only at room temperature are elevated temperatures. X is converted to Y, Y is converted to X. There is interconversion, that therefore these are interconvertible stereoisomers. The stereoisomers which are interconvertible at room temperature are at elevated temperature. Those isomers are said to be conformational isomers. So this is the exact definition of configurational isomers and conformational isomers. Now, in order to understand geometrical isomerism, you have to know about rigidity of bond, flexibility of the bond. First, let us take a bond rotation. CC bond rotation, single bond rotation I am taking. So this is the example. Here the molecule is represented in wedge dash formula. If you carefully observe in this wedge dash formula, this carbon, methyl group is in the plane, methyl group is in the plane here. At this center, bromine is below the plane, at this center, bromine is above the plane, and here hydrogen is below the plane and hydrogen is above the plane. So what is the rotation we are talking about? Bond rotation, it is not a molecule rotation. We are talking about a bond rotation. In order to understand this bond rotation, this is the molecule we are talking about. You just hold this position. Imagine an axis which is passing through carbon-carbon bond. Hold this position and rotate this particular carbon either in clockwise direction or in anti-clockwise direction by 180 degrees. rotate right hand end of the molecule through 180 degrees. So you are holding this position, and around this CC bond, around this bond, this position, this part of the molecule is rotated by 180 degrees either in clockwise direction or in anti-clockwise direction. That is your wish. So after rotation, since this position is held, there is no change, but here there will be change. Orientation will be different. Here you can see methyl group is in the plane but below the carbon, but now methyl group is still in the plane but above the carbon. Bromine is below the plane, now bromine will be above the plane. Hydrogen is above the plane, and here hydrogen will be below the plane. So whenever the molecule, it is once again, it is not the rotation of the molecule, it is rotation of bond. Here you can see the model. The two balls which are black in color are the carbons, and each carbon is attached to hydrogens. Left side carbon hydrogens are shown in green in color. Right side carbon hydrogens are shown in white in color. So here we are talking about CC bond rotation. It is not the rotation of the molecule, it is CC single bond rotation. For the sake of convenience, you can see one position is held same and another position is being rotated. For the sake of convenience, I am rotating the molecule like this, and the two carbons both are shown in black color. Now we are talking about a CC bond rotation. One position is held same. Now I am going to rotate the adjacent carbon. By keeping one carbon same, another carbon is being rotated around CC bond either in clockwise direction or in anti-clockwise direction. But here I am rotating in clockwise direction. So you can see how carbon and hydrogens are moving, and this is called CC bond rotation. CC single bond rotation, there is a free rotation. There is a free rotation. Position of one group, orientation of groups of one carbon remains same. Orientation of groups of another carbon are getting affected. So this is called CC bond rotation, CC single bond rotation. You can see how the molecule is having CC single bond rotation in this. The two carbons both are black in color. One carbon is held same, another carbon around CC single bond I am going to rotate in clockwise direction. Orientation of hydrogens which are shown in white color remains same, but you can see hydrogens which are shown in green color, their spatial orientation is getting affected, and this is called CC bond rotation. It is not rotation of molecule, it is CC bond rotation. One more example you can observe. So this is the molecule we are talking about, and here this carbon position is held, and around this particular bond I am going to rotate this carbon around this particular bond either in clockwise direction or in anti-clockwise direction by 180 degrees. If you see, this COOH is in the plane but below the carbon. After rotation, that COOH will be still in the plane but that will be above the carbon. OH before rotation, that is lying below the plane, but after rotation that will be above the plane. So orientation of groups at one carbon are getting affected, and that is due to CC single bond rotation, and this is called a free rotation of CC single bond. So here if you see the some points, here we can say some bonds rotate easily, but others do not. Bonds which can be rotated freely are called as the flexible bonds or rotatable bonds. Just now we discussed the CC single bond, that is flexible bond or a rotatable bond. Bonds which cannot be rotated freely are called as rigid bonds or non-rotatable bonds. That means bonds are classified into two types. They are flexible or rotatable bonds, rigid or non-rotatable bonds. If you see the examples of flexible or rotatable bonds, the single bonds present in open chain, we already discussed, that is said to be an example of flexible or rotatable bonds. Single bonds present in closed chain, CC double bond or CN double bond or CO double bond, whatever it may be, double bond and triple bond. Single bonds in closed chain, double bonds and triple bonds, these are rigid or non-rotatable bonds. Now, let us try to understand why double bond, triple bond, single bonds present in closed chain are rigid or non-rotatable bonds. We'll try to understand. But most importantly, if you take rigidity of double bonds, for example, ethene molecule we are taking, ethene molecule. So here this is internuclear axis. Perpendicular to internuclear axis, there are p orbitals, whether they are px px or py py or pz pz, whatever it may be. This is internuclear axis. Perpendicular to internuclear axis, p orbitals are undergoing sidewise overlapping. Therefore, there will be pi bond above and below the internuclear axis. If you try to twist at this position, since there is another bond between those two carbons, that bond will undergo cleavage. You can see whenever you try to rotate this particular carbon CC bond, so what happens, the p orbitals will be moving in opposite plane. As a result, the pi bond will be cleaved, overlap, destroyed. So exactly you can see this is the sigma bond, internuclear axis. Perpendicular to that, due to sidewise overlapping, there is one more bond. And if you are trying to rotate this particular carbon around this particular bond, so what happened, this overlapping will be broken. This bond will be broken because this will be remain in the same plane, but this is changing its orientation. So CC double bond free rotation is not possible because perpendicular to sigma bond there is a pi bond. If you want to rotate, first this pi bond has to be cleaved. At room temperature, that amount of energy is not available. Therefore, CC double bond, not only CC double bond free rotation is not possible in double bond. Therefore, double bonds are said to be non-rotatable bonds, or these are also said to be rigid bonds. Rotation about a double bond does not readily occur. It can happen only if pi bond breaks. But pi bond definitely requires some energy. So the energy barrier to rotation about a carbon-carbon double bond is nearly 62 kilocalories per mole. So this bond rotation is possible only after cleavage of pi bond. That is possible when you supply 62 kilocalories per mole. But at room temperature, that amount of energy is not available. Therefore, CC double bond is rigid. You can see exactly when you are trying to rotate this particular portion around that particular bond. So there is another bond. This particular pi bond will prevent the free rotation. Therefore, double bonds, not only double bonds, even triple bonds are rigid bonds. They are also known as non-rotatable bonds. Now let us see the situation of CC single bond of ring system. I am talking about CC single bond present in the ring system. You can see totally there are 6 bonds. These 6 bonds, any single bond you take, since it is locked in closed system, CC bond free rotation is not possible. That free rotation is possible only when this bond undergoes cleavage. For example, if the bond undergoes a cleavage like this, then it becomes open chain compound. In case of open chain compound, CC single bond rotation is definitely possible. But the energy required for the cleavage of this particular bond is very high, that is not available at room temperature. Therefore, the single bonds present in ring system, single bonds present in ring system are definitely rigid. That rotation around that particular single bond is not possible. These two have same molecular formula, same connectivity, but here methyl group is above the plane, here methyl group is below the plane, and these two are said to be stereoisomers, but this cannot be converted to the second one. So these are non-interconvertible stereoisomers. Those stereoisomers are said to be configurational isomers. So CC double bond, CC triple bond and CC single bond of ring system, all these bonds are rigid bonds, non-rotatable bonds. Now finally, let us talk about stereo center or stereogenic atom. Stereo center, it is an atom at which the interchange of two groups generates a stereoisomer. Let us understand. This is one example given, and this is another example with the same structure but different spatial orientation. For example, you take this particular carbon atom. Here bromine is above the plane and hydrogen is below the plane. In the second representation, bromine is below the plane and hydrogen is above the plane. In order to generate the second one, you have to interchange the orientations of bromine and hydrogen. Of course, they are attached to same carbon, but here bromine is above the plane, but here bromine is below the plane. You have to interchange the orientation of bromine and hydrogen. As a result, you will get the second configurational isomer. So the atom at which the interchange of two groups or atoms generates a stereoisomer, that particular atom is a stereogenic atom, or that is also known as a stereo center. So here in this example, so this is the stereo center. Of course, you can also do the same operation at this center. So this is also stereogenic center, but in this example, we changed the orientation of bromine and hydrogen at this carbon. You can take one more example. So this is one example given. And here you can see methyl group and hydrogen. Here methyl groups are same side, here methyl groups are opposite side. In order to generate this particular configurational isomer, we have to interchange the orientation of methyl and hydrogen. You are interchanging the spatial orientation of methyl and hydrogen of this particular carbon. So this particular carbon is said to be stereo center or stereogenic center, because this center is generating a stereoisomer. And here one last example let us take. Here we have a carbon with four different groups. One is alkyl group, hydrogen, NH3 plus and COO minus. You can see here alkyl group is in the plane, here also alkyl group is in the plane. COO minus below the plane, COO minus below the plane. But here NH3 plus is above the plane and hydrogen is in the plane. You are interchanging the orientations of hydrogen and NH3 plus. As a result, you are going to get a stereoisomer of the given compound. So this particular center is responsible for the generation of stereoisomer. Therefore, this is called stereogenic center or stereo center. So these are the various subtopics, and these subtopics are very much helpful to understand the concept of geometrical isomerism, and some questions related to geometrical isomers will be discussed in the coming videos. Thank you very much.